So this is about convection, heat transfer. And so the physics underlying convection is that hot surface, whether it's a pipe or a tank or whatever, the thing that you're trying to cool, it's conducting heat with the first layer of air touching it. Okay? So the whole idea behind convection is that you are not happy with that rate of heat transfer. The next layer, the layer of air that's sticking to the pipe or to the tank or to the whatever, the wall, is probably going to get very hot very soon, and therefore there will be not that much temperature difference between the hot air and the hot wall. And so the air will not suck that much heat out of the wall. So what is the chance, or what's the way to improve that conduction? If only the temperature difference is much bigger. If only we can replace that hot layer of air with a fresh cold layer of air, that probably will get even more conduction out of the wall. So I'm just keep stressing the fact that the first layer is conducting with the pipe. All right? It's temperature that we are worried about. And ideally, you would like to have this temperature T infinity. Ideally, you would like this temperature of the next layer to be T infinity, but it's not going to be T infinity, right? T infinity is only really far away. This would be T infinity. All right? So T infinity would be only here. But here in this place, it's going to be probably a little bit hotter. It will be closer to Ts. All right? And that is the problem. So that's why you keep replacing that layer of air, either by forced convection, because you are blowing in it with a fan, or if this thing is basically just sitting on a surface, a hot surface by itself, it will rise, because hot air have lower density, make it more point. All right? So this is called natural convection. This is called natural convection, and if you are blowing with a fan, then it's called forced convection. All right? So you can tell probably that natural convection is not really a good mechanism, right? Because you leave your food on the table and it takes forever for it to cool down. But if you really put a fan into it, that happens really quickly. All right? So we will not really depend that much on natural convection unless we are forced to. When there are an application where there's just no place for a fan, or you really want it to be quiet over there, you don't want the noise associated with the fan, but chances are we are going to depend on the forced convection. All right? And so there are two chapters on forced convection. One of them is called external convection. That's when the air is moving outside the surface. And there's internal convection. That's when the air is moving inside a pipe, inside a duct. So that's internal convection. Both of them are forced convection. Both of them will be driven by a fan or a pump, whether the air or the liquid or the crude oil. All right? And what's our job in these chapters? All those chapters is basically to get Q convection, the watt per meter square, or if you put area over here, then this would be Q dot convection, and then it will be in watt. You would like to get the rate of convection. So you can tell this phenomena is very complex fluid mechanics / heat transfer interaction. You need to get this right, you have to solve the fluid mechanics too. You need to know how much momentum is moving, or basically how quickly is the air is moving on the surface. And then you solve the temperature profile of this air layer as well, so that you can tell what is the temperature profile on the wall, and therefore you can solve for what's now the improved heat transfer coefficient, or what's the improved heat transfer rate. So they overcome or jump on all of this and basically say, you know, let's actually just say that the convection is sum H multiplied by delta T time area. What delta T? Ts minus T infinity. Ts would be this 50 over here, and T infinity would be the air far away from the surface. All right? So that layer next to the surface is not really at T infinity. It's probably a little bit hotter, in case we are trying to cool a hot surface. But they just basically say H will take care of this. If we find this H, you multiply this H by this delta T times the area, and that will be the Q in watts. All right? Or H delta T, this is going to be watt per meter square. All right? And all those formulas, all those 3 chapters is basically just to try to figure out what is the H that will do this magic. That you multiply by delta T, Ts minus T infinity, and that would be the Q getting out. Okay? So, how do they do this? So those formulas, you know that anytime you try to come up with a formula that is that has units, or if I basically tell you that H is 5 watt per meter square Kelvin for a flow over 5 by 5 meter square plate with air at 20 degree and 5 meter per second, you know that this number will be different if this plate is a little bit bigger, or if the air velocity is a little bit stronger, right? You can tell that the H, if the air is moving very slowly, probably will have different H than air that's moving very quickly, right? So that is wrong. That's what's wrong with having formula that has units. But if I give you a formula that's dimensionless, chances are it will hold for different geometry, different air velocity, different fluids. All right? So that dimensionless formula for the H is called the Nusselt number. So that Nusselt number that you see over here is basically dimensionless H. So rather than watt per meter square Kelvin, the Nusselt number is dimensionless, just like the Reynolds number. What's the unit of the Reynolds number? Nothing, right? It's dimensionless number. So the Nusselt number is, you can think about it as H delta T over K delta T over L, or basically HL over K. What's H? That's the heat transfer coefficient that we are looking for. What is K? That's the K of the air, not K of the plate. All right? And what's L? That's a length scale coming from the problem. We'll talk about this L. We need a length scale that will get this H over K to be dimensions, because we know H is watt per meter square Kelvin and K is watt per meter Kelvin. So there is 1 meter missing here. That L will fix this problem, and it will make it dimensions. But when you look at that definition, H delta T over K delta T over L, that's as if we are saying Nusselt number is Q convection over Q conduction. Exactly. All right? So if we turn off the air, let's cut off the fan. Let's even prevent the air from rising because of gravity. Can we do this? Yes, we can. Go to outer space. The people in the space station, their computers are being cooled by not natural convection, not forced convection. The air is not moving. The hot air just set on the computer. Doesn't want to go anywhere. Actually, my PhD advisor, he actually did experiments on the space shuttle. That last space shuttle, the Columbia space shuttle that crashed, those astronauts were doing experiments for him the night before they crashed, actually. All until the doctor basically that was monitoring their heart, they told them, you have to stop, this is too much, you are getting tired. So he did a lot of experiment on the space shuttle on flames, and when you turn on a flame in the space shuttle, if you turn on a flame over here in this classroom, like a candle flame, how does it look like? It's pointed, right, and it's rising up. Guess what? Because of the buoyancy. Because hot gases coming from the combustion go up. But when you burn it in space shuttle, how do you think it will look like? It's spherical. All the flame are spherical because the combustion product doesn't know where to go. So they go up or down or right or left, they don't know where to go. So they just basically make spheres. All right? So it's the buoyancy, it's the gravity that make the things, when they are getting lighter, to go up, and when they are heavier, to go down. All right? So if we are in the space shuttle and there's no convection, there's no fan also running, and there's no natural convection, guess what would be the Nusselt number? Free homework if you tell me that's right. No? What did you say? L? No.
1.
And you, Brandon, get a free homework.
Someone listens.
Exactly. I guess he's wise to wait. So, so Brandon said Nusselt number would be 1, or basically saying Q convection is exactly Q conduction. It's basically as if when you try to calculate the Q convection, or what the Q being sucked by the air, it's exactly the Q without any air moving. It's just Q conduction. The first layer of air is conducting, and the second layer of air is conducting with the first layer, and the third layer is conducting with the second layer. There is no extra. But if we turn on the fan, if we let gravity take the air and rise and bring fresh air, we expect the Nusselt number to be who said greater than 1? Excellent. What's your name? Jay is saying it will be greater than 1. So the Nusselt number, if you are in the exam and you calculate Nusselt number less than 1, know something is wrong. All right? The Nusselt number for any convection problem need to be 1 or higher. All right? Because we are basically adding, we are boosting the mechanism that will transfer heat. Yes?
Now, is there any scenario ever that the Nusselt number would ever be less than 1? Any scenario?
I cannot imagine.
Okay. That means gravity could do all kinds of weird stuff. Right?
No, I cannot imagine, because it's either you help this layer to get out,
Right.
or basically you just leave it, and it's basically doing the conduction business. All right? Just the question was, is there any scenario that Nusselt number should be less than 1? No. If you ever get Nusselt number less than 1, go back and check your numbers. All right? It also cannot be negative. Never. Right? So H is not defined to be negative. H is always. So that means that you have, when you write this Q convection, then you have to say T high minus T low. You cannot just say it's always Ts minus T infinity, and therefore the H could be negative. No, if it happened that the surface actually is cold and the air is hot, the equation for Q convection would be H T infinity minus Ts. So don't give me H that's negative. It's not defined like this. Right? So you flip the temperature if the hot side is actually the air, not the surface. And you would say Q convection is H T infinity minus Ts. Okay? All right. So if there is no convection, just pure conduction, this would be the Q dot. The air here will have a temperature profile like this. All right? And Q would be minus K partial T partial Y, and the Nusselt number would be 1. Okay? That's pure conduction. So now what will happen if we have convection is that temperature profile, the K air partial T partial Y that will look linear like this, will end up being replaced by a boundary layer profile. All right? This is, so what I'm plotting here, this is the velocity. If you had your fluid 1, and you should have fluid 1, otherwise you are not in this course, you shouldn't be in this course. You know that the velocity U will look to be something like this on a plate. Why is it 0 here? The velocity is 0 here because right, it's taking the to the surface, because on a small scale, if we open this under a microscope, no matter how smooth the surface is, in real life it's actually pretty rough on a molecular level. And those first layer of molecules are actually here. They are trapped. They have no choice but to move with the plate, because they are really in the plate, kind of. Right? That's why they are sticking to the plate. So that is the first layer. So U fluid is basically U wall. And so if the plate is not moving, the air is not moving. If the plate is a wing or a submarine surface wall, then the fluid is moving with that wall. Right? So that is the first layer. How about the second layer? Why the second layer is also kind of not really moving? I mean, it's moving, but not that much. Why? Say that again, I couldn't hear. But what is the mechanism? So Mallory is saying because the first layer doesn't want them to move that quickly. What do you call this interaction between the layers stuck to the wall and the next layer to it that are not allowed to move that quickly?
That's the friction caused by the viscosity.
That's the viscosity, right? That's the viscous effect. That's basically the sticking force between, and the more sticky the fluid is, if it's honey, it will behave differently from ethanol, right? The more sticky the fluid, the more their layers are basically glued to each other. All right, and so that's why the next layer, this one is 0, this one will have a little bit higher velocity, the next layer will have a little bit higher velocity, the next layer will have, and so you'll end up with that velocity profile. All right, of course, if the fluid is not that sticky, they will behave as if they are disconnected with each other, right? So if the fluid is not that sticky, what it will look like? It will look like this, right? Only the first layer is stuck, but then the next layer is actually moving much quicker because they don't really see the need that they need to stick to the next guy. Okay? So that is called a boundary layer. And if you take 4273 experimental fluid mechanics, you would hear more about how to come up with that velocity profile. Actually, we solve for that velocity profile, and you know exactly how much friction does this thing generate and how can you use the shear stress, right? So there's a whole course to study this fluid mechanics motion. But the point is, I'd like to take from here is that there is a velocity profile, all right? And that velocity profile depends on the viscosity of the fluid, how sticky it is, or basically on the mu. What's mu? That's the viscosity of the fluid, all right? What's the unit of that mu? Pascal second. What's Pascal? That's Newton per meter square, all right? So this is called viscosity or dynamic viscosity, because there is something called kinematic viscosity. Does anyone remember what is a kinematic viscosity? What symbol did we give it to kinematic viscosity? Gamma? No. Huh?
They're both.
No, the dynamic viscosity or the viscosity in short is mu. The kinematic viscosity is, it's nu. It's called nu. Right? When I was undergrad, I used to really confuse the two of them. You know, especially because my language is not Latin, so I couldn't really remember, is this one mu or nu? Until one day it hit me that this guy actually looked like capital N, and this guy looked like capital M. So from that point on, every time I look to this, I see capital N, and immediately I'm telling myself that's mu. And every time I see this guy, I basically think, well, this is a capital M, it's mu. So I never confuse that, and I made that discovery myself. No one told me about this. So now I don't confuse them. That's mu and this is mu. Anyway, that kinematic viscosity, mu, is mu over rho, right? And they also call it the momentum diffusivity, just like alpha, the thermal diffusivity. Jason had a question in the break for me. He said how we can calculate alpha in the program, because the program asked for alpha. That software, the SST conduct that we are going to use in the project, he asked for alpha.
Oh, we have the rho.
Right, because alpha has a definition with K, rho, and Cp. If you know K, rho, and Cp, you can calculate alpha. And what's the unit for alpha? Excellent, meter square per second. The same as nu. Nu also has the meter square per second. Actually, the two of them really represent, from the fluid point of view, they represent the same thing. They represent diffusivity of energy or diffusivity of, so alpha is the thermal diffusivity or diffusivity of energy, and nu represent the diffusivity of momentum. It's basically how the momentum is transferred from one layer to the other. Again, how sticky the fluid is. So there is actually a dimensionless number. That's the ratio between the two of them. And that number is going to be with us in all the convection formulas. That number is Prandtl number. So the Prandtl number, PR, is the ratio between those two guys. And so the Prandtl if the Prandtl number of order of 1, what does it mean? It means that the thermal diffusivity and the momentum diffusivity, they are of the same order of magnitude. The fluid, whether it's air or glycerine or honey or crude oil, if the Prandtl number is 1, he diffuses the energy the same way he diffuses momentum. If the Prandtl number is really high or it's very low, that means that no, he has preference in which of them he diffused pretty quickly. All right. So for gases, you should expect the Prandtl number to be around 0.7. So that means gases is basically almost have the same alpha mean. For liquid metal, we will see how does the Prandtl number will look like. All right. But keep this in mind that that Prandtl number is basically, he will tell us that, we'll see the definition in a second, but he will tell us the ratio between the alpha and the mu. All right. Okay. One thing also I'd like to say is that, so you see this. If I can get my colors in the thing. If you see this, the other velocity profile, this one, the blue one over here, and the red one, those guys have different boundary layer thickness. What is the boundary layer thickness? So the boundary layer thickness is basically the distance it takes from the surface to reach the free stream velocity, or say capital U. So the velocity, say here, is 10 meters per second. That's the velocity away from the wall, 10 meters per second. So it takes the fluid a certain height before he reaches to that 10 centimeters per second, right? So theoretically speaking, the fluid will reach 10 meters per second at infinity, theoretically speaking. But to reach 99% of that U, you will take, say, 4 millimeter, 5 millimeter in air and water. Okay? This is the boundary layer thickness. This is how much distance does it take to almost be in the free stream velocity. Alright? So you can see that blue guy in here. This would be its boundary layer thickness, or basically the distance it takes to reach to almost U infinity, or 99% of U infinity. And the red velocity profile take much longer distance to actually go there. So those two velocity profile actually are for two different modes. One of them is called laminar velocity profile, the other one is called turbulent velocity profile. Why this is important? Because when we try to solve the convection heat transfer, when we try to pick up the formula that we calculate the H, and that's what we really will do. I'm not going to ask you to drive those formulas yourself. It's not like the conduction, when we had the general equation of conduction and we integrated it ourselves and we came up with the temperature profile. Over here, you will be given sets of formulae for different convection, and all you have to do is basically to pick the right one to calculate the H out of it. Alright? So which one you will choose, you will be facing choices. Is the flow is laminar or is the flow is turbulent? Is it a flow over a flat plate or is it a flow over a cylinder? So those are the choices that you will make. And once you identified, I think this is the flow over a cylinder, and I think the flow is laminar, you just pick the formula for this guy and you will calculate the H out of it. And then you will go and say Q convection is HA delta T. Done. The problem is over. Alright? So it's important to identify whether it's laminar or turbulent. So what is laminar and turbulent? So laminar, that's when the flow is moving in layer, one layer after the other. Turbulent, that's when the flow is moving with very rapid motion. So not just like they are moving a layer one after the other, but there is this huge kinetic motion. All right? They actually, the guy who, Reynolds was the one who made these experiments. Let me jump to those experiments and show it to you. So he basically, and we actually do this in experimental fluid mechanics course. We actually have a water channel and we put dye in the water, food color basically, and we let the water move very slowly, and you can see the dye really is doing this. It's moving in very smooth line. And once you increase the velocity a little bit, you will find out the dye is jumping up and down. All right? So there's something that basically when the velocity starts being higher, that basically triggered this chaotic motion. So it's not just one layer sliding over the next one, but the whole thing is basically moving up and down. So basically turbulent flow means very rapid mixing. All right? So you can also see this when if you are a smoker, don't smoke, but if you are a smoker, you'll be able to see the smoke basically moving very slowly, and then after a while it be totally chaotic. All right? So is this good for heat transfer or not? Or basically, is it good for convection? Will it improve the convection from the pipe surface if it's turbulent, or will it decrease the convection? It will, right? It will increase the convection. Because what was the point of convection? We wanted to move this hot layer from the wall, replace it with a new layer, and that's why we were always trying to change the layer next to the wall. Well, turbulent will do this for you. He will take the whole thing and just bring fresh air, fresh water, and put it on the... So turbulence is really good from the heat transfer point of view. It's bad, however, from the fluid mechanics point of view, because you can guess it will increase what? That it will increase the shear stress at the wall and therefore increase the drag. Or if it's a pipeline, it will increase the pressure drop. So if you have a heat exchanger and you are trying to remove the heat by fluid, it will take the pump more power to pump the water when it's turbulent than when it's laminar. But they will be able to remove a lot of heat when they are turbulent than they are laminar. All right? So there is this, so I'm telling you there will be this huge mixing, but don't get confused that the average velocity would be still in this direction. All right? So the average velocity would be, the fluid is moving to the right, but on top of that, on top of the fact that he's moving to the right, he's also moving up and down very rapidly. So if you're just putting your finger here and you are measuring that velocity, you will see the temperature and the velocity and everything that you measure jumping up and down. But on average, of course, there is an average. All right? That's what he's trying to say over here. That if we measure the temperature or the velocity or anything at one point in the boundary layer, turbulent boundary layer, you will see this variation. So this variation, this fluctuation in the temperature and the velocity, this is called the turbulent intensity. That's a big deal in turbulence. That's basically how do they measure the turbulence level. So when we have a wind tunnel over here in main hall on the fluid lab in 2118. So when we bought that wind tunnel from the company, they were really very happy to tell us that, you know, we guarantee that the turbulence fluctuation is less than, and they would give you a number. They would say it's less than 10%. So they are saying that in our wind tunnel, if you measure the velocity, that fluctuation will be less than, say, 10%. So that say that, well, see, we don't have that much turbulent flow in our wind tunnel. The air that we provide for you in that wind tunnel will be almost uniform. There is not that huge variation. All right? Very good. So that velocity profile that I'm plotting for you is the average velocity profile, okay? That's if you put your finger for 5 minutes and you average for 5 minutes, that would be the average velocity profile. But know that on top of that, there is this huge variation up and down, right and left. So without reading the names on the graph, don't read. Which one you think is laminar velocity profile and which one is turbulent? The blue or the red? Which one is turbulent?
Okay.
Because you read or because you know?
Because it takes the rate at which it goes up.
So Jesse is right. The red is the turbulent velocity profile. And the reason why it's the turbulent velocity profile is because he managed to bring, look at this. He managed to bring very high, ouch. He managed to bring very high velocity near the wall. Compared to the laminar, that the velocity near the wall is very small, right? The velocity of the wall is very small, but the turbulent, the velocity near the wall is very large. Why it's very large near the wall? Right, Jesse say because the air is already moving. It's not just he depends on the viscosity to start moving one layer after the other. No, he actually take the velocity from the top, put it at the bottom. And he will do the same thing for the temperature. All right? So we should expect the turbulent heat transfer to be higher than the laminar heat transfer rate. All right? Because he will bring the cold T infinity and put it very close near the wall. All right? Now, notice one thing. The boundary layer thickness, or the height of the boundary layer, is bigger in which case? Turbulent or laminar? You can see in the drawing, the turbulent boundary layer height is actually bigger. Right? Look at this. So he brings the fluid velocity all the way down to the wall, but he also take the wall effect all the way up, meaning more and more layers are noticing that there is a wall down there and their velocity is affected. So the idea is that turbulence make the fluid very well connected. The top hear about the bottom hear about the top. So you get very high velocity near the wall and you get the wall effect all the way up. Right? Okay. Very good. So those would be important physical understanding that will help us later. All right. So again, all our job in this 4 chapters actually, but we will leave the natural convection till the end of the course. So we'll do the forced convection first, and then we will do natural convection later at the end of the year. All right? It's not because I'm trying to push for the heat exchanger design to come quickly because that will be your second project. So then after I give you your second project, then we'll have time to actually go through the natural convection. I'm not saying it's not that important. There are certain applications where it's just natural convection and you just have to depend on it. But it just for a lot of industrial application, it's forced convection. Right? So that's what we are going to do. We are going to say Q is HA delta T. The whole problem with convection, you'll have to use this equation. So whenever you have a problem with convection and you don't know what to do, just write Q equal HA delta T and probably you'll get 4 out of 10 just writing this. Right? So 40% just writing this equation. And the only trick is, well, what is H? Let's try to find the formula for H. And there will be a lot of them, you'll get lost probably. Which one to pick? All right? So that he in this chapter actually will try to calculate this H later in the next chapters, because you can tell that, if I try to calculate the heat transfer over a cylinder, you probably have seen those pictures, when there is huge chaotic motion behind the cylinder. We call it a wake. So solving the fluid flow around this and then getting the temperature profile around it so that we can calculate the gradient, so that we can calculate the Q out of this. It's really long process and it requires a lot of resources, right? So they probably will depend on experiments. So you will see for the rest of the 2 chapters, 7 and 8, there will be a lot of empirical formulae. They will tell you, we just measured the H, and when it turned out that it's function of the Nusselt number. We said the H will be given in a Nusselt number, right? Form. So the Nusselt number is function of another dimensionless number. Can you guess what dimensionless number? Excellent. What's your name? Jacob is saying the Nusselt number will probably be function of the Reynolds number. Why did he think that? Because he probably think, well, the H is function of the V. The heat transfer by convection will probably be function of how quickly the air is moving. And the velocity is in the Reynolds number. Right, so the Nusselt number will always be function of the Reynolds number multiplied by another dimensionless number. Free homework problem, if you remember. I actually said this number earlier today. Prandtl number, and you had a free homework. Why did Mallory said the Prandtl number? Because we said the Prandtl number is the ratio between alpha and nu, thermal diffusivity and momentum diffusivity. So when Jacob said the Nusselt number is function of the Reynolds number is just telling you how does the velocity look like, how does the fluid mechanics is doing. The Reynolds number, if you remember, rho Vd over mu. It's inertia force over viscous force. Reynolds number basically tell you is the flow is laminar or turbulent, the dynamics of the fluid mechanics. But to move it to temperature and conduction, heat transfer, you need to transfer that velocity profile to temperature profile. And that's where the Prandtl number will show up. So all those formulas will be basically Reynolds multiplied by a Prandtl. All right? To multiply by constant, to a power of constant, and those constants all come from experiments, right? And those will be most of the formula, and that will be a lot of experiments, and will be very complicated, especially when you have a bunch of cylinders. So usually when you have a radiator in your car, open your radiator today, go home and open the radiator, find that it's not just one cylinder in air. There's a bunch of cylinders. There's a lot of fans. I mean, the whole thing is just a mess. To solve this fluid mechanics part, that's a lot of calculation. So they will have to depend on a lot of experiments to do this. All right? But when the geometry is very easy, we can actually do it analytically. We can actually calculate this. And that's what he will do today, and that what will be the quiz for tonight. Okay? So we will do it. I will show it to you how they do it, and then I'll ask you to do it on a quiz too, to calculate the H. Right? We have a lot of time, don't worry. We have 30 minutes, and then we'll have the quiz in the last 10 minutes. So let's see how he can actually so we'll do it. We calculate the H only today, or only in this chapter. But later on, we will just have to use a lot of experimental formulae. Nusselt is function 0.5 multiplied by Reynolds to power 0.1 times the Prandtl to power 0.5. That's for a square cylinder. Now for a circular cylinder, it's another coefficient, another power. All right? Even natural convection, when there is just a hot plate and the air is rising because of the heat, it will be not really Reynolds number, but it will be the same concept. Some kind of a heat, a number that tells us how quickly the air is moving, multiplied by a Prandtl number. That's the essence of convection. You make the air move, and he take the heat with him. So it's a Reynolds number multiplied by a Prandtl number. All right? So the strategy to calculate the Q convection is, the strategy is actually to say that Q convection, that you're going to say that it's H times Ts minus T infinity. Really at the wall, at the first layer, whether the air is moving or not. In both cases, whether the air is moving or not, still the first layer is conducting. All right? The air movement is just changing the temperature profile at the wall, but the first layer is always conducting. So Q convection is Q conduction, let me say it's Q conduction at, if this is Y, so it's at Y equals 0. All right? Okay. Now Q conduction at Y equals 0, and I'm not talking about the metal, I'm caring about the fluid, would be minus K fluid, partial T, partial Y. So if only someone give me the temperature profile here. So the temperature profile could be something like this, if Ts is hot and T infinity is cold, or is going to be something like this, if Ts is cold and T infinity is hot. But there will be a temperature profile like this. And that gradient, that partial T, partial Y, the slope of that line at the wall multiplied by minus K, that is Q conduction per unit area. Area normal to the Q, right? So this Q convection by definition, let me put 3 lines here. This Q convection by definition is H T S minus T infinity. This is actually, this equation is the definition of H. This is how they come up with this H. And then they will say, now let's do experiment to come up with that H. But H is defined such that when you multiply by delta T, you can get the Q, leaving the wall by conduction. Is that clear? Question about this? All right. So what is the strategy then to come up with H from this equation? Anytime you have an equation and you are looking for one parameter in it, to get this one thing, that H, you have to get everything else, right? This is how you can get the H out of it. So we need to get everything else. Actually, Ts is known, T infinity is known, K fluid is known. What is not known is, what we don't know? Partial T, partial Y. Not anywhere at Y equals 0. So really to come up with that H, they need to get the temperature profile at the wall. Okay? Or basically you need to solve the temperature field. Alright? So then they can differentiate it and say, at the wall it's equal to 5. Let's multiply by the K. Here is our Q. Alright? So that's what he says over here, that then the H eventually become minus K partial T partial Y at Y equals 0 over Ts minus T infinity. You just put H in one side, everything else on the other side. All right? Now, that temperature profile, you can guess that the temperature profile, what I'm plotting here, ouch. This is the plate, all right? I'm not saying it's insulated, I'm just plotting the wall. So as the air come here fresh, U infinity and T infinity, he start growing this boundary layer. So meaning that the velocity here is probably like uniform like this, not knowing that there is a wall. And then when start seeing the wall, a boundary layer will grow. So one part will start feeling the fluid, while start feeling the wall, while the rest of the fluid doesn't even realize there is a wall there. And that boundary layer thickness get bigger and bigger and bigger as more and more of the fluid will start hearing about that wall. Or the viscosity basically start moving this effect. Alright? Or if there's turbulence, the turbulence takes its time to spread this wall velocity and temperature. So what I'm saying is that that temperature profile and that velocity profile will grow bigger and bigger as we are moving along the plate. All right? They start very small and then they end up being very big. So the boundary layer grow basically. So what I'm saying then is that the gradient at the wall is not going to be the same everywhere on the wall. It will change from the start till the end. Does this make sense? Right? So if partial T partial Y at Y equals 0 at the wall is different here, than here, than here, what does it tell you about H? H is different from different location, right? So if I just interested in the overall H, so this is going to be the quiz. I will ask you for the H all over the plate. And so I'll give you a formula for H at a different location. Which one will you use? If I give you H as function of X, and then I ask now for the whole plate, what is the H? Right. Now what kind of average? Mathematical average, should we just add all of them and divide over the total?
Integrate H with respect to X and
Right.
divide by X.
Right. This is the average. You integrate, if it's continuous function of X, not discrete function of X. He didn't give you the X at the beginning and X of the end, so that you add them and divide over 2. No, he gave you H as function of X. So averaging them mean that you integrate over X and you divide over L. Right? And that would be the average H throughout the whole thing. All right? So the average H would be the local H dx from 0 to L, and then you divide over L. All right? Why H is varying from one place to the other? Because look at the definition. The definition is H is the local gradient of the temperature at the wall. That local gradient will change with the boundary layer from one location to the other. Right? He's trying to explain this over here. They actually managed to get the velocity profile by putting smoke line or dye line. So as this thing grow over a pluff body like this, you can see how the boundary layer, if I plot this, so I would say, I'm trying to gauge it with my eye, but so the boundary layer, thickness basically change from one location to the other, right? And therefore, the temperature profile also will change. So this is called the boundary layer thickness. And again, in experimental fluid, and actually in our textbook, but I don't want you to worry about the derivation of the boundary layer. Let's leave this for a fluid mechanics course. But you can solve the equation that govern the fluid mechanics and come up with this delta as function of X. Over here, let's just look at the solution of this. But you can guess what are the name of those equations. Can anyone guess what are the names of those equations that solving them will give us delta? Anyone? What equation do you need to solve? Equations do you need to solve to come up with delta? Start with an N. N-A-V-I-E-R. Dash S-T-O-K-E-S. Anyone? Navier-Stokes equation. Did anyone hear about Navier-Stokes equation? Navier-Stokes equation is basically the equation that control the fluid motion over a plate in a pipe, over an aeroplane, over a submarine, right? Those are the equations that control the fluid mechanics, right? And so solving them will actually give you the flow here in the laminar. So now once the flow just like the smoke coming from a cigarette, after a little bit, those layers start basically those kinetic motion and it become turbulence. All right? And so once it become turbulent, they are not moving in layer anymore. They are basically going up and down and right and left, and there is this huge mess everywhere, and that's called turbulent. All right? So it takes time to do this, or it takes distance. If you have external flow on a flat plate or over a submarine or inside a pipe, there is a certain length before this thing start growing and become turbulent, right? So we'll skip this part, but basically he's saying that the viscous effect is really very clear in this part. Near the wall, when you see the viscosity is doing this, making the flow go from 0 until U infinity, the viscous effect is very important here. But once you go outside this boundary layer, the velocity hardly change. It's as if the flow doesn't have viscosity. It does, but it's not that important because he's not really shearing against each other. There's not that velocity profile. They are just moving as if they are sliding against each other. There is no really interaction between the two of them. All right? So there is something called external flow and internal flow. External flow, that's the flow around surfaces, around an airplane, around a submarine, around a cylinder. And there is internal flow, that's when we go inside a cylinder, inside a duct. So that's chapter 7 and this is chapter 8. And we'll have the formula for each one of them. There is a course over here in OSU, it's called MEE 3293. I actually teach that course too. And that's compressible flow. So there's a whole course for compressible flow. And that's when the fluid starts changing its density. Of course, liquids are compressible or incompressible? Incompressible, right? Liquids are incompressible, meaning that it's very, very hard to change their density. It takes tons of pressure to make the density of the water change the least bit. So we consider liquid are incompressible. But also air can be considered as, and of course you would think, well, air is compressible. I can, if this thing is filled with air, I can squeeze as much air as I want inside this thing. It's compressible. But we can treat air as incompressible, and that's what we are going to do in this course. We will treat the air as incompressible, meaning the density will not change on us for most of the problems. When it changes, I will tell you. But we will think it's incompressible as long as the Mach number is less than 0.3. And when I was undergrad and my professor told me this, I thought this is totally meaningless. What do you mean that if they are moving less than 30% of the speed of sound, then I am incompressible? That didn't make no sense to me. It's as if basically you are telling me if the moon is in the sky, you should be happy. What is the relation between the moon in the sky and me being happy? Well, but it's the trick is that they shouldn't really have said this. They should have said that's just a conspiracy to confuse students. They should have said the speed of a pressure wave, a small magnitude pressure wave. If he have said this, then it would have made sense to me, because then you are telling me if you are moving, what could change as a fluid, as liquid? What could change my density? Pressure, right? If you put pressure on me, I will get squeezed, my density will change. So if you are telling me, if you are moving faster than the speed of a pressure wave, it's one thing. If you are moving slower than the speed of a pressure wave, it will be something else. Yeah, that makes sense now, because it's basically, you are telling me, will you be able to escape from the thing that will try to pressure you or not? Right? So the pressure wave is basically what tries to change your pressure. That sound wave that we are talking about, why did they pick sound wave? Because it's just the most famous low magnitude pressure wave. That's what the sound wave, the acoustic speed. It's a small pressure wave. Right? When I talk, I pressure the air, and that air start pressuring, the pressure go up a little bit, and then it go hit your drum. That pressure, that increase I'm putting in the air, make your drum basically move. Because you remember the force is pressure times the area. So you will hear more when you go to this course. You will really understand what's going on. But basically, if you are moving less than 0.3 of the speed of sound, that means that the pressure wave will always catch you and adjust your pressure. That make you incompressible. All right? So low moving air or low moving gases, low speed moving gases can be considered as incompressible. If they are start moving very quickly, higher than 0.3 of the pressure wave, acoustic pressure wave, and that's how much? 340 meter per second in air. 346 meter per second. So in most application, we move lower than this. We move less than 100. That wind tunnel we have in Min Hole, the maximum velocity there is like 60 meter per second. So it's definitely less than 100 meter per second, which is 0.3. So we think that air moving in the wind tunnel basically have the same density, 1.2. Okay? More when we take that course. All right. the other thing too you would like to talk about is the viscosity. So if you try to calculate the shear stress on the wall, it's mu partial u partial y. So that velocity profile, if I'm plotting u here, the gradient over here, partial u partial y at y equals 0 multiplied by the viscosity, that would be the shear stress. So this is turbulent boundary layer, this is laminar boundary layer. Ouch. Let me draw a good job. So here is the turbulent boundary layer, and here is the laminar. So which one do you think will have more shear on the wall? The turbulent or the laminar? So partial u partial y, if you are thinking that partial u partial y is this slope, you are wrong. Partial u partial y is this. Because it's as if I'm saying partial y partial x. Well, this is y and this is x. So the slope is really this. So partial u partial y is higher for the turbulent, meaning the shear stress is higher for the turbulent. It makes sense. You can see that turbulent velocity profile over here. No, he is like really very high velocity near the wall. He's going to move the wall away from how quickly he's moving near the wall, right? He's about to rip that wall away because he's just bringing so large velocity near the wall. So, and mathematically also much universal line is actually this. So this is smaller compared to this for turbulent. Okay? So the gradient is higher for turbulent. So that's why turbulent is great for heat transfer, but from fluid mechanics point of view, from shear stress point of view, it's bad because it will decrease the shear. Right? So when they have a submarine, they can actually make it move much faster if only they can make the wall laminar or turbulent. If they can make the flow around the submarine laminar. So actually my office mate, his PhD was about how we can make the flow on a submarine laminar all the way. Of course, that's really hard because the submarine is very long, right? And so chances are you will hit this very quickly. This point, by the way, does anyone remember from fluid 1? When will it, actually no, you didn't really have it in fluid 1. You will have it in fluid 2 or experimental fluid mechanics. It takes a certain unit number to come here, 2, 10 to power 5, correct. In the pipeline, it's different. In the pipeline, it's 2,300 from the Moody chart. But on a flat surface, it's 200,000 unit number. But that's not really a large number because nu by itself, remember what's Reynolds number? U x over nu. Or if you want rho, u x over mu. Remember rho over nu over rho is nu. So my point is that air viscosity is already 10 to minus. What's mu air? Does anyone know? 10 to minus 5. So between u and x, you have to come up with just the 2. So if you are moving at 10 meters per second, you are done actually in the first. Very quickly you will become turbulent. So his PhD was how we can actually preventing that turbulence from kicking in. How we can keep it laminar as long as we can. You understand why? Because laminar boundary layer will have less shear. Right? So he's also saying that the viscosity, we think of viscosity as being constant all the time, like what's the viscosity of oil, what's the viscosity of honey, what's the viscosity of water, and we think it's actually a function of temperature, right? The viscosity is a function of temperature. That's why they heat sometimes very viscous oil to let it go through the boiler or the furnace. You know, it's very hard to boil it, to pump it when it's cold, but when you heat it a little bit, and in the oil industry, when they have this really very sticky, heavy oil, how they can condense the oil to come up? They send very hot steam. They send very hot steam inside to heat the oil, make it less viscous, because as you heat the oil, the temperature will make the viscosity go down. So the shear stress would be much smaller. It would be easier to pump. Right? Especially when you are dealing with very heavy oil, like the one in the candidates and the very heavy oil with sand, they push steam, very hot steam, and that helps the oil to become less fluid. More fluid, I'm sorry. We make it more fluid because it makes the viscosity smaller. Alright? So we should expect the temperature to drop for liquid. However, the viscosity increase for gases as you heat it. Right, amazingly, and that is because the mechanism of momentum transfer in liquid is different from gases. So in gases, the layers interact with each other when they collide with each other. Those air molecules, when they hit each other, they figure out, you are moving much faster than me, maybe I should move faster. So they only come in contact with each other when they collide with each other. So the frequency of collision depends on how quickly they are moving. Well, how quickly they are moving, and I'm not talking about the average velocity in the flow direction, I'm talking about the thermal velocity in everywhere. So the air here in this room, even if we turn all the air inlet and the air outlet, and we just live in one box and no one is breathing for 5 minutes, so that the air molecule set, no, they will not be setting. They will still be moving. They will move with the thermal fluctuation. All right? And so this depends on their temperature. The quicker they move, the faster their temperature, and the higher the temperature will be. All right? So as a result, as we increase the temperature of the gas, they will collide more, and therefore the viscosity will increase. The information will be conducted, or basically communicated, much faster if they are hotter. But that's not the case for liquids. All right? That's what I'm trying to explain over here. And we talked about kinematic viscosity and how it's mu over rho. And the shear stress can actually be written as dimensionless shear. That's the friction coefficient. So that CF is the shear stress over half rho u squared. And if you remember, this half rho u squared is called the dynamic pressure. All right? And that's the Reynolds number, rho Vd over mu, or basically Vd over nu. So that D is a pipe, in case there's a, if this is a pipe, that would be the diameter. If this is a flow over a flat plate, the length scale that makes sense is the x, the distance from the leading edge. So the Reynolds number here is defined as Vx over nu. That's the length scale that makes sense in the problem, is the plate is 5 meters or 5 centimeters. But when you have a flow in a pipe, it's the diameter that makes sense. Makes sense to the fluid. I mean, that's what affects the fluid motion. All right? And here that's when he say, just like the momentum boundary layer that takes the velocity from 0 to infinity, there is a thermal boundary layer that takes you from Ts to T infinity. All right? And this is the Prandtl number. This is going to show up in all equations that involve the Nusselt number. The Nusselt number will always be some kind of Reynolds number multiplied by some kind of Prandtl number. The formula that I'm going to give you for the H will have those guys. Will have the Nusselt number and next to it a Prandtl number. What's the Prandtl number? Nu over alpha, or basically mu rho Cb over K. So actually there was rho over here and rho over there, and they cancel it. Okay, and so mu over rho, that is nu, and Cb rho over K, that's the alpha. Right, and then they cancel the alpha, the rho, and it end up being mu Cb over K. Actually, if you just open the tables, your thermo book, or actually this book, you will find the Prandtl number for different gases at different temperature. Because alpha and nu is function of temperature, as you understand now, right? The more you heat the gas, the more you expect alpha and new to change. Right, and he's actually telling us that, see, for gases, look at the Prandtl number. Almost 1. That means that the gases move the heat or the energy, thermal energy, the same way he moved the momentum. But liquid metal and oils, glycerine, you will have different ratio of, maybe one of them conduct heat very well, but it does not really conduct momentum. So some material are a little bit selective in the way they do it. We had this experiment in my lab in HRC where we actually were supposed to heat a chamber that has polymer. We would like to keep this polymer liquid, so we have to heat it, because if we make it cold, he will solidify from us. But we would like to have this polymer under a high voltage. So we wanted to heat the polymer with an electric heater, but we don't want to mess with its electric potential. We want it to be, because we report in the experiment what is electric voltage. So we had this insulated material that is really amazing. So it allowed the heat to go through, but still it's electrically insulated. All right? So some materials are selective in the way they move different modes of energy. All right, and we talked about laminar and turbulent. And see over here, it's, I guess, Y. Is the length scale that makes sense. Sorry. When you say whether it's laminar or turbulent, it's not the diameter of the candle, for example. Right? So different problem will tell you, or you will have to guess what is the length scale that makes sense. So for example, if you have a flat plate like this and the air is moving in this direction, it's this x that makes sense to use in the news number, not the width, right? Because that width is just basically a repetition of the same velocity profile. That boundary layer will basically repeat itself across different slices of the plate. So it's only the x that makes sense. All right. Sometimes this is actually the most difficult part of the problem, is to identify what is the length scale that I should use in the Reynolds number. And here he explained laminar against turbulent. And this is when he said that there's all those turbulent fluctuation. And actually, there are ways to come up with that solution. You know, it's not totally impossible. I don't want to give you the impression that those turbulent or those wakes behind cylinders is not solvable. It just takes time to solve them. And so if you give the engineer an explicit formula, empirical formula, that he will just immediately calculate the H, he will be very happy, rather than spending 5 hours trying to solve the velocity profile around the cylinder so that he can get the gradient, so that he can get the Q leaving the wall. But there are ways to solve them, and let's leave this for fluid mechanics course. And this is the boundary layer and how it's like really different from laminar than turbulent. And here he tried to solve the boundary layer. See, this is the, he tried to solve the boundary layer to come up with the velocity profile. So this is the boundary layer equation. This is a simplification of the mothership of the Navier-Stokes equation, which is the mother of all fluid mechanics equation. So there's a simplified Navier-Stokes equation, so they can come up with this. And even this is not that easy to solve, because you can see it is partial differential equation that make it really hard to solve, right? But they solve it, and once they solve it, and they also can come up with a similar temperature, a similar equation to get the temperature, or energy equation, right? I don't want you to solve those equations. Let's leave this for other courses. But I'm just telling you that the solution exists, and we will just use that solution. And they are solving it using, I mean, it's still partial differential equation. So they have to turn it into ordinary differential equation. That's one trick to solve partial differential equation. We know this trick, right? Remember in the unsteady solution, we did this trick. We turned the partial to ordinary differential equation. So they do this, and the guy who did this is called Clausius. He actually did his PhD over this. He was a student of Prandtl, and he came up with that solution. How to turn the partial differential equation into ordinary differential equation. So the velocity is just function of one variable. So rather than x and y, no, it's one variable now. Let's call it eta. But rather than the velocity, he's also solving for something called f, dimensionless number or function, that later he will get the velocity out of it. And he solved it, and he ended up getting the velocity profile and the temperature profile. And once he get the temperature profile, now he can do his dream, right? And do the partial t, partial y at y equals 0. And again, that temperature profile that I'm going to give you in a second is not going to be the same everywhere. It's going to be function of x. It's different from the start till the end. At every x, it's different. Partial t, partial y is different. It's function of x. That's why the h, look at that. It's function of x. And as promised, I did promise you that the h will be function of Reynolds and Prandtl. Here is the Prandtl. Do you see the Reynolds number here anywhere? Almost, right? Remember, it's Vx over nu. V nu x. Almost the Reynolds number. Well, when we turn this h into Nusselt number, we will get the Reynolds number. Because how do you turn this h into a Nusselt number? Hx over k. So you multiply the whole thing by an x, you will end up with Vx over nu. That is the Reynolds number. So as promised, Nusselt number is, this is a flow over a flat plate. All right, laminar flow. This is the easiest. I guess this is the only problem really they can solve it analytically, right? And so they end up with a constant 0.32, and the power is half, and the power is 1/3, and that's an analytical solution. For more complicated problem, those numbers will be different, and we just have to get them from table that were generated from experiments. All right? So how do we use this formula? If you are interested in the flow, in the heat transfer here in this place, you just substitute this x. Again, Reynolds x is x v over nu. And the Prandtl number, and that would be your h at this place, hx. Now the q leaving this place would be h delta t. What's delta t? Ts minus T infinity. This is if you are interested in the q leaving only this part. What if you are interested in the whole q leaving the plate, as you should be? You integrate over the whole plate. Does this make sense? Ask me now, because the quiz will basically, I will give you the h, I will tell you what is q leaving the whole plate. Say that again, I didn't get the question. All right, so this is the h, right? This is hx, this is the convection heat transfer coefficient at a certain x. That's why you call it h sub x, because h here is different from the h here, is different from the h here, because we realize the temperature profile is different. Okay, the formula that they will generate, rather than telling you the hx is basically this, they rather have it in dimensionless form. So rather than giving h, they will multiply this h by x and divide over k air. Now this x h over k, by definition, it's called the Nusselt number. And so they will report the Nusselt number as this. So this came just from multiplying this equation here by x and dividing by k. So this equation again is analytical, but later on you will be given similar equation but with different coefficient that came from experiments. Starting with today's quiz. Today's quiz is actually an experimental correlation, but it's still its function of x. So it's different from one x to the other. And so if you're interested in the h overall, the average h, you shouldn't be happy with h at the beginning of the plate or at the end of the plate. You should be happy with the average h. How you are going to get the average h? Integration, h dx over dl. So h average is hx dx over L. That's what you will do. And so once you get this h average, and then he asks you for the q, you would say q is h average a ts minus t infinity. Does this make sense? That's really what we are going to do for the rest of the 3 chapters. We will come up with a formula that will give us h, and we multiply by a delta t to come up with the q. There are variations on this problem. I mean, he can give you the q and ask for the area, or he can give you the area and the q and ask for the temperature of the air. That will do this. I mean, right? Ready? Not yet? Why? What's annoying? You will integrate, you multiply by a delta t, you will get the q. Okay? You know how to integrate the square root of x? Because that's what it boiled down to. You know how to integrate x to power 1/2 dx? Anyone? X to power 3 over 2 divided by 3 over 2. And what about x to minus 1/2? How do you integrate x to power minus 1/2 dx? So it's x 1/2, and you divide, you always add 1 and you divide on the new power. All right.